Okay, so for the next two lessons, we're going to be taking a look at how I can use a arithmetic in a geometric sequence and write a rule to represent those sequences so we can use them as prediction. Okay, so what we're going to do is we're going to look at two different types of formulas. The first is called recursive and the second is called explicit. Okay, so in a recursive formula, each term is found by doing something to the term immediately in front of that term. So for example, if we take an arithmetic sequence 2, 4, 6, 8, what is happening to each of those values as they are increasing? So if you notice, each term is found by adding 2 to the term before it. So for a recursive definition, we are going to take whatever term, so some term, okay, and then we are going to take the previous term, and we're going to then add 2. Okay, so for example, let's suppose that we take the first term. So this is a sub 1, okay, and this is a sub 2. So how do I get the value of the second term? A sub 2 is equal to, and I'm doing that kind of out of place. I'm getting ahead of myself because, sorry about that, I forgot I had a sub 2 right here. So a sub 2 is equal to whatever a sub 1 is plus 2. Well, a sub 2 was 4. The first term was 2. And if I take 2 plus 2, I get 4. So is 4 equal to 4? Yes, it is. The third term is equal to the second term plus 2. So the third term, if I go up here, here's a sub 3, was 6. The value of the second term was 4. And 4 plus 2 is 6. So that checks out. Okay, so if I wanted to find the sixth term, I need to know what the value of the fifth term is, and then I would just add 2 to it. Okay, well, do you know the value of the fifth term? Not technically. I only have in the sequence up to the 4th. So to get the 5th, I have to add 2. So I'm going to say for the 5th term, so a sub 5 is equal to an additional 2, a sub 6 as then an additional 2. So the 6th term is equal to 12. Okay, so all you're doing is add 2 as many times as necessary to find the missing term. Okay, so how about A100? Well, A100 means that I am looking for the 100th term. Well, that means that I need to know, if I know the 99th term, I can just add 2 to it. But do I know the 99th term? No, I don't. I don't know the 99th term. I don't know the 98th or the 97th. The next closest term I have is 6, the 6th term. So I could keep going. I could say, all right, well, the 6th one is 12. Then I know 14, then 16, then 18, then 20, then 22, then 24. All right, well, that's the 7th, 8th, 9th, 10th, 11th, 12th. That's only the 12th term. And I need to get to the 100th term. This is where there are some drawbacks, okay, or some disadvantages to the recursive formula. The recursive formula only works if you know the term previous to it. Only works when you know previous term. Or for smaller numbers. I could get to the 100th term, but it would take me for a long time. Okay, so this takes too long. So then what we have is another option, and that is the recursive formula, the explicit formula. So if we look at, sorry, I forgot I gave you some examples here. So find the recursive formula for each arithmetic sequence. The recursive formula is just taking whatever term plus the term previously before it plus the common difference. Whatever the common difference is what I'm adding or subtracting, okay? So in this case, my numbers are getting smaller. So remember, D is equal to negative 58 minus negative 28. So that means I have negative 30. So we are subtracting by 30 for each one of these values, which means that my recursive formula is the nth term is equal to the term before it, so n minus 1 minus 30. And that's the recursive formula for this particular sequence. Okay, in this one, so the common difference is 17 minus a negative 3. It's a positive 20, so a sub n is equal to a sub n minus 1 plus 20, because this time I'm increasing my values in my sequence by 20. Okay, if I look at the other ones, negative 40 to negative 38, I'm taking a negative 38, D equals, minus a negative 40, that's add, so that's a positive 2. So whatever term is equal to the term before it plus 2. So if I add 2, I would get to negative 32. If I add 2, I would get to negative 30, so on and so forth. Okay? All right. So that's how you use the arithmetic, or that's how you use the recursive formula. The problem is, if I want to know the 10th term, I would have to do this. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I would have to continue adding by 2 until I got there. Okay, so then thankfully we have what's called an explicit formula. The explicit formula helps you find any term in a sequence quickly as long as you know the first term. Okay, so here's my specific my explicit formula. Whatever term I'm looking for, so this is the term I want, is equal to the first term plus the common difference times n minus 1. Okay, n is the, sorry, I kind of mislabeled there. It's not the term I want, it's the value of the term I want, because n is the term number that you want, that you're looking for. Okay, so for example, I notice that I am increasing by 9. Okay, so my common difference is equal to 9. That means I'm going to add 9 a whole bunch of times. Remember that multiplication is just repeated addition. Hence why this part here has a multiplication, because multiplication is repeated addition. Okay, so when I look up here, how many times did I have to add 2 from this value to get to the 10th term? Well, I had to add 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. To get to the 10th term, I had to add 9 times, which is 1 less than what term I was looking for. Okay, that's why there's the n minus 1. And I have to start somewhere. So remember, the initial value is like our y-intercept when we're talking about graphing linear equations. An arithmetic sequence, because I'm adding the same value every single time, is just like a linear function. Okay, so when I'm writing the equation for the arithmetic sequence, here's what we're going to do. We're going to start with a sub n, so that's any term, the value of the term is equal to the first term. So a sub 1 is equal to 8. The common difference was equal to 9. And n in this case is going to be any term. So because I'm not looking for anything specific right now, my equation is going to be 8 plus 9 times n minus 1. Sometimes you will see it written this way. Other times you will see it simplified. So the simplified version looks like this, where you have to distribute that 9 to both sides. So we get 8 plus 9n minus 9. And then I combine my like terms. All right, that's a sub n. And so I get a sub n is equal to negative 1 plus 9n. This would be the simplified version, and this is more traditional. Okay, so both are okay. Sometimes you will see it in a simplified form though. Okay, and doesn't this look familiar? Here I have an mx and a b starting at a negative 1 with a common difference or rate of change of 9. So this is really similar to everything that we've done in linear equations. Okay, so then let's do a couple more examples. So all we need is we need the value of the first term. We need to know what the common difference is. So the first term is 1.3. The common difference is equal to the second minus the first. So this is 3.8 minus 1.3, which is 2.5. So there's my d value. So a sub n is equal to 1.3 plus 2.5 times n minus 1. If I simplify, then you're going to see a sub n is equal to 1.3 plus 2.5n minus 2.5. Okay, and then 1.3 minus 2.5. 1.3 minus 2.5. We get negative 1.2. So a sub n is equal to negative 1.2 plus 2.5n. Okay. Now we can use our knowledge of creating explicit formulas to find any term. So if I want to find the 50th term, so in this case, a sub 1 is 31. The common difference, so I'm at 24 minus 31, the second minus the first, is equal to negative 7. We are looking for, in this case, n is equal to 50 because I am looking for the 50th term. So I would say that a sub 50, the 50th term, is equal to 31 plus negative 7, and actually I'm going to erase that. I'm going to make that 31 minus 7 times 50 minus 1. And so be careful with our order of operations here. Remember PEMDAS. We should do what's in parentheses first. So 31 minus 7 times 49. Then we need to multiply. So we're going to do negative 7 times 49. And we get negative 343. And we're going to take 31 minus 343. Not one, no, sorry. Calculator. 31 minus 343. and we get negative 312. So the 50th term is negative 312. Now you have to ask yourself, does that make sense? Well, yeah, these numbers are decreasing, going down, going down. I only have a couple of values left to go, decreasing by 7, before I start getting negative. And this is going to get more and more negative. Okay, so this number being as large and as negative as it is, it makes sense that it would be that way. Okay, all right, and then lastly, here's just a couple more examples. Find the explicit formula. For these, I'm not necessarily going to simplify, but so we add 10, we add 10, we add 10. So there's my common difference, and my a sub 1 is 21. So a sub n equals 21 plus 10 times n minus 1. If you'd like to leave them that way, you can, or you can simplify. And this would become a sub n is equal to 11 plus 10n. So either of these are okay. These are equal. Okay, and I think in IXL, both answers are acceptable. Okay, so when you go through those assignments, in here, I'm just going to do this one more time. So I'm subtracting 2 each time. So D is equal to negative 2. My starting value is 9. So A sub n is equal to 9 minus 2 times n minus 1. So if you want to simplify it, 9 minus 2n plus 2. So don't forget your signs. This is a negative times a negative. And so 9 plus 2 is equal to 11 minus 2n. So a sub n is 11 minus 2n. This is an equivalent. So these are equivalent. Okay? All right. So that's explicit formulas for arithmetic sequences and also the recursive formula. Okay? All right. Have a great day.